Apache Flink is a distributed data processing framework optimized for both streaming and batch processing. Its hallmark is its ability to process unbounded and bounded datasets with high throughput, low latency, and fault tolerance. Built for real-time analytics, Flink is a popular choice for applications like fraud detection, IoT data handling, and log processing. For more tech interview materials, please visit our website OOzie8.com. Core components include 1. Job Manager, central component that orchestrates the entire Flink application, responsible for scheduling tasks, resource allocation, and monitoring execution progress. 2. Task Managers, worker nodes that execute the actual computations of the job. Manage task slots, which represent a subset of resources for parallel execution. 3. Data Stream API, core API for stream processing, supporting transformations like map, filter, join, and window operations. Handles unbounded data streams in real time. 4. Dataset API, API for batch processing of static, bounded datasets. Supports complex transformations like grouping, joining, and aggregation. 5. State Management, Flink supports stateful stream processing, allowing operators to maintain intermediate results across streams. State is stored in state backends like RocksDB or in memory for fast access. 6. Checkpointing, Flink creates consistent snapshots of application state at defined intervals. Stored on external systems like HDFS or S3 for recovery during failures. 7. Connectors, integration with external systems such as Kafka, Elasticsearch, Cassandra, and HDFS for data ingestion and output. 8. Flink Runtime, executes jobs by translating them into physical execution graphs and distributing tasks across the cluster. What happens under the hood? 1. Execution flow. A job submitted to Flink is converted into a logical DG, directed acyclic graph. The DG is optimized and transformed into a physical execution graph, which is split into tasks for parallel execution. 2. Stream processing. Flink processes events in real time by applying operations on streams. Uses watermarks to handle late-arriving events in event-time processing. 3. Fault tolerance. Checkpoints are used to periodically save state. If a node fails, Flink resumes processing from the last checkpoint. 4. Batch processing, transforms batch jobs into a series of streaming operations for optimized execution. 5. Parallelism, Flink achieves scalability through parallelism. Tasks are divided into subtasks and executed on multiple task managers. Example use cases are real-time fraud detection, analyze financial transactions in real time to identify suspicious patterns. Log and event analysis, process server logs and application events for operational insights and alerting. ETL pipelines, continuous extraction, transformation, and loading of data for analytic systems. Ad targeting, deliver personalized advertisements based on real-time user activity. Advantages include 1. Unified framework, supports both real-time stream processing and batch processing, eliminating the need for separate systems. 2. Low latency, processes data streams in milliseconds, making it ideal for real-time applications. 3. Fault tolerance, checkpointing and state backends ensure jobs can recover seamlessly from failures. 4. Scalability, designed for distributed systems, Flink scales horizontally to handle large workloads. 5. Rich ecosystem, provides integrations with numerous data sources and sinks, including Kafka, Cassandra, and HDFS. Limitations include 1. Complexity, steep learning curve for developers unfamiliar with distributed systems and stream processing. 2. Resource intensive, stateful processing and checkpointing can demand high memory and storage resources. 3. Operational overhead, requires significant effort to configure, deploy, and monitor in production. 4. Debugging difficulty, distributed tasks and real-time environments can make issue diagnosis challenging. Thanks for watching. For more tech interview materials, please visit OOzie8.com. Apache Goblin is an open-source distributed data integration framework designed for scalable, flexible, and robust data ingestion. It specializes in moving and transforming data from various sources to target systems while handling challenges such as data quality, format conversions, and scheduling. Goblin is widely used in large-scale data pipelines for systems like data lakes, analytics platforms, and machine learning workflows. For more tech interview materials, please visit our website OOzie8.com. Core components include 1. Source and extractor. Source defines the data to be fetched, including its type and location. Extractor fetches the actual data, transforming it into records Goblin can process. 2. Converters. Handle data transformations to change record formats, e.g., JSON to Avro, or clean data before delivery. 3. Quality checkers. Ensure data meets predefined quality standards, including schema validation and threshold checks. 4. Writer. Moves processed data to the target storage systems, such as HDFS, S3, or Kafka. 5. Speculative execution. Handles retries and fault tolerance by re-executing failed tasks in parallel. 6. Scheduler. Manages job orchestration, defining when and how often data ingestion jobs should run. 7. Metrics and monitoring. Built-in tools for tracking job performance, data ingestion rates, and error rates. 8. Pluggable architecture. Highly extensible with plugins for custom sources, transformations, and writers. What happens under the hood? 1. Configuration. Jobs are configured via YAML or Java-based APIs. Each job defines the source, transformations, and target system. 2. Task execution. A job is broken down into tasks, which are distributed across nodes for parallel execution. This ensures high throughput. 3. Data transformation. Data passes through converters and quality checkers for format changes and validation. 4. Fault tolerance. Failed tasks are retried based on defined policies, ensuring data integrity. 5. Output delivery. Once processed, data is written to the target system. This could involve partitioning or writing to different data sinks. Example use cases are data lake ingestion. Ingest and normalize data from multiple sources, e.g., databases, logs, into a central data lake. Real-time streaming. Move data from Kafka streams to HDFS or cloud storage. ETL workflows. Automate extraction, transformation, and loading of data into analytics platforms. Data format standardization. Convert raw data into structured formats like Avro or Parquet. Advantages include 1. Scalability. Designed to handle large-scale data ingestion pipelines across distributed systems. 2. Flexibility. Supports diverse data sources, transformations, and targets. 3. Fault tolerance. Robust mechanisms for task retries and speculative execution. 4. Extensibility. Easy to integrate custom plugins for specific requirements. 5. Operational simplicity. Job orchestration and monitoring are built in. Limitations include 1. Complexity. Steep learning curve for configuration and deployment. 2. Resource intensive. Requires significant computational resources for large-scale pipelines. 3. Limited real-time support. Primarily focused on batch processing with limited real-time capabilities compared to alternatives like Apache Flink. Thanks for watching. For more tech interview materials, please visit OOzie8.com. Apache Impala is an open-source, massively parallel processing MPP SQL engine for data stored in Apache Hadoop. Unlike traditional MapReduce-based SQL tools, Impala provides low latency, interactive querying for big data, making it an excellent choice for real-time analytics. It integrates seamlessly with Hadoop's ecosystem, querying data stored in HDFS, Apache HBase, or object stores like Amazon S3 using SQL. For more tech interview materials, please visit our website OOzie8.com. Core components include 1. Impala daemon, Impalad. The core query execution component. It runs on each data node in the Hadoop cluster and executes query fragments. 2. Impala State Store, status stored. Tracks the health and availability of Impala daemons and maintains a registry for query planning. 3. Catalog service, cataloged. Manages metadata, ensuring that Impala queries are aware of changes in the underlying datasets, e.g., schema updates. 4. Hive Metastore integration. Impala uses the Hive Metastore to store table definitions and metadata, enabling compatibility with Hive-based tools. 5. Query Planner and Optimizer. Converts SQL queries into efficient execution plans, optimizing for parallel processing. 6. Storage layer. Queries data directly from HDFS, HBase, or cloud storage without duplicating it. What happens under the hood? 1. Query parsing and planning. SQL queries are parsed by the query planner, which generates a logical execution plan optimized for MPP execution. 2. Query fragmentation. The execution plan is divided into fragments distributed to multiple Impala daemons for parallel execution. 3. Execution. Impala daemons execute their assigned fragments by reading data from HDFS or HBase directly. 4. Aggregation and result merging. Partial results from each daemon are merged, aggregated, and returned to the client. 5. Metadata management. Impala retrieves table schema and metadata from the Hive Metastore and caches it in the catalog service for faster access. Example use cases are real-time analytics, power dashboards or applications that require sub-second query responses on large datasets, exploratory data analysis, enable data scientists to run SQL queries on massive datasets without moving data into separate analytic systems, ETL acceleration. Use Impala for fast transformations of raw data into a more structured format. Log and event analysis. Analyze server logs or streaming event data stored in HDFS or cloud storage. Advantages include 1. Low latency query performance. Sub-second query times for interactive analytics. 2. Hadoop ecosystem integration. Reads directly from HDFS, HBase, and object storage without requiring data duplication. 3. SQL compatibility. Familiar SQL syntax enables easy adoption by analysts and data scientists. 4. Massively parallel processing. Efficiently utilizes distributed computing resources for large-scale data analysis. 5. Multi-tenancy support. Supports multiple users and queries concurrently. Limitations include 1. Resource-intensive. High memory and CPU requirements compared to batch processing tools. 2. Not ideal for small clusters. Performance benefits become apparent in larger clusters. 3. Limited fault tolerance. Queries may fail if a daemon becomes unavailable during execution. 4. Dependence on Hive Metastore. Relies heavily on Hive Metastore for metadata management, adding an additional layer of complexity. Thanks for watching. For more tech interview materials, please visit OOzie8.com. Apache Kylin is an open-source distributed analytics engine designed to deliver near real-time SQL querying capabilities on massive datasets. It is specifically optimized for online analytical processing, OLAP, enabling multidimensional analysis over data stored in distributed systems like Hadoop, HDFS, or cloud storage. Kylin builds pre-computed data cubes that significantly accelerate complex queries, making it ideal for scenarios like business intelligence, BI, reporting, and analytics. For more tech interview materials, please visit our website OOzie8.com. Core components include 1. Query engine. A SQL interface to execute fast, multidimensional queries on pre-computed data cubes. 2. Cube engine. Creates pre-aggregated OLAP cubes from raw data. Cubes store summaries of data across multiple dimensions, enabling rapid query responses. 3. Metadata store. Centralized storage for cube metadata, schemas, and configuration. This is typically backed by relational databases like MySQL. 4. Job engine. Manages distributed tasks to build and refresh cubes using Apache Spark or MapReduce. 5. RESTful APIs. exposes a programmatic interface for integration with BI tools, dashboards, and custom applications. 6. Storage integration. Supports distributed data sources like HDFS, Hive, and cloud-based systems. What happens under the hood? 1. Data preparation. Users define dimensions and measures for analysis by Kylin's user interface or configuration files. 2. Cube building. Kylin scans raw data from the source, e.g., Hive tables, aggregates it across the defined dimensions, and stores the pre-aggregated cubes. 3. Storage. The pre-aggregated cubes are stored in columnar storage systems like HBase for optimized retrieval. 4. Query execution. When a SQL query is received, Kylin's query engine matches the request with the relevant cube and retrieves results directly from the pre-computed data. 5. Integration. Results can be visualized using BI tools like Tableau, Power BI, or Apache Superset. Example use cases are business intelligence reporting, accelerate dashboards and analytical tools for enterprise reporting, customer analytics, analyze behavior, purchasing patterns, or preferences at scale, financial reporting, enable multidimensional financial analysis with near real-time updates, IoT analytics, summarize and analyze streaming sensor data for actionable insights. Advantages include 1. Near real-time querying. Pre-computed cubes allow sub-second query response times on massive datasets. 2. Integration with Hadoop ecosystem. Seamless compatibility with Hive, HDFS, and other Hadoop components. 3. SQL support. Enables non-technical users to interact with big data using familiar SQL. 4. Scalability. Efficiently handles petabytes of data using distributed storage and compute resources. 5. BI tool compatibility. Works well with industry-standard business intelligence tools. Limitations include 1. Pre-computation overhead. Cube building requires significant time and resources for large datasets or frequent updates. 2. Data cube explosion. The storage required for cubes grows exponentially with the number of dimensions. 3. Limited real-time analytics. While fast for querying, data updates are not real-time but depend on cube refresh schedules. 4. Complex configuration. Requires expertise in cube design, data modeling, and Hadoop integration. Thanks for watching. For more tech interview materials, please visit OOzie8.com. Apache OOzie is a workflow scheduler for managing Hadoop jobs. It allows users to define, schedule, and execute sequences of Hadoop jobs in a coordinated manner. OOzie integrates tightly with the Hadoop ecosystem, orchestrating jobs across frameworks like MapReduce, Hive, Spark, and Pig. Designed for data pipeline orchestration, OOzie ensures tasks run in the correct sequence based on dependencies, time triggers, or external events. For more tech interview materials, please visit our website OOzie8.com. Core components include 1. Workflows. Directed acyclic graphs, DGs, that define a series of tasks and their dependencies. Written in XML, specifying actions, e.g., MapReduce, Hive, custom Java programs. 2. Coordinators. Trigger workflows based on time schedules or data availability. For instance, run a workflow when a new dataset arrives. 3. Bundles. Group multiple coordinators for higher-level management of complex pipelines. 4. OOzie Server. The central component responsible for executing workflows, managing dependencies, and coordinating job execution. 5. Client interface. Command line tools or REST APIs for submitting and monitoring workflows. 6. Action nodes. Define specific tasks to be performed, such as executing MapReduce jobs, running a Hive query, or sending emails. 7. Control nodes. Manage workflow logic like forks, joins, decisions, or error handling. What happens under the hood? 1. Workflow submission. Users create an XML-based workflow definition and submit it to the OOzie server. 2. Execution orchestration. The OOzie server evaluates dependencies and triggers actions in the specified sequence. 3. Job monitoring. OOzie tracks job execution status and manages retries or error handling for failed tasks. 4. Coordinator triggers. Workflows are initiated based on time, e.g., every hour, or events, e.g., file arrival in HDFS. 5. Output. Workflow results are written back to HDFS, Hive, or another target system, ready for downstream processing. Example use cases are data ingestion pipelines. Automate ETL workflows for loading and transforming data into HDFS. Daily reporting. Schedule Hive queries and Spark jobs to generate daily or hourly reports. Event-driven pipelines. Trigger workflows based on the arrival of logs or new datasets in storage. Complex job chaining. Define multi-step pipelines combining MapReduce, Spark, and custom tasks. Advantages include 1. Native Hadoop integration. Work seamlessly with HDFS, MapReduce, Hive, Pig, and Spark. 2. Flexible workflow management. Supports conditional branching, retries, and error handling. 3. Event-based triggers. Enables dynamic workflows based on data availability or external events. 4. Extensibility. Custom actions can be integrated using Java programs or shell scripts. 5. Scalability. Manages workflows across large, distributed Hadoop clusters. Limitations include 1. Complex configuration. Workflow definitions in XML can become cumbersome for large pipelines. 2. Limited usability for non-Hadoop jobs. Best suited for Hadoop-centric environments, less optimal for broader data ecosystems. 3. Error handling limitations. While retries are supported, debugging complex workflows can be challenging. 4. Manual monitoring. Lacks advanced visualization tools compared to modern orchestration frameworks like Apache Airflow. Thanks for watching. For more tech interview materials, please visit OOzie8.com.